Recording is rolling. So Tuesday, September 21st. Yeah, you guys were just watching Paul Hewitt on a bed of nails. Well, had bed of nails going on. You guys were saying that you would rather lie on a bed of nails that had 1,000 nails rather than one nail. And here's why. You guys said that your weight would represent some kind of force, like a down force. If you rely on one nail, that would be a really tiny area. And so that would be a huge pressure. Versus if you rely on 1,000 nails, well, each one takes a little bit of your weight. So the pressure would be very small, distributed. And pressure is also involved in a hydraulic lift. So the idea of hydraulic lift, say you have some mechanism like this, it's filled with some fluid, maybe water, maybe some other kind of fluid, and you're trying to lift, let's say you're trying to lift this car. Ooh, now this is a really heavy car. I give it a mass of 2,000 kilograms, which means it has a weight on Earth of about 20,000 newtons, because go from mass to weight multiplied by about 10 meters per second squared. You guys know that. So that means that I need a force from this piston right here to push up with 20,000 newtons just to hold it up. What if I want to raise this car? Like, you could do that actually with a really tiny input force. The idea is something called Pascal's principle. It says that the pressure in this fluid is going, well, it's think about it like this. It's going to distribute like this. Down here at the bottom, isn't the pressure equal at equal levels, right? Equal depth. You go. What about at this level? Isn't the pressure equal at equal depths right here? What if you go up to like this level, like this dashed in cross-sectional area versus this? That's about the same height. I bet those have the same pressure there too, right? That's getting a little bit less as you go up. But hey, what about the pistons? Wouldn't this pressure pushing up on this piston have to equal this pressure acting up on this piston? Because it's one continuous fluid, isn't it? One continuous mass. Pascal's principle says that the pressure is going to distribute like that. So the pressure on the left piston has to be equal to the pressure on the right piston. And since pressure is just force per unit area, you guys know that, right? Newtons per square meter. That would be what it's measured in. It's called Pascal. 1 Pascal is 1 Newton per square meter. You can set up this ratio. You can say that force to unit area has to be the same ratio from left to right. All right, so let's break out some more paper. Let's throw some numbers on this. I wonder what this down force has to be to push this car up. And actually, it's a really tiny force. So the force on the left side divided by the area on the left side is equal to the force on the right side divided by area on the right side. I gave you 3 of these 4 different values. Solve it for what is the input force? What is this force on the left side? You know that the left side has a cross-sectional area of 1 square meter. It's about 9 floor tiles. Think of it like that. So start plugging in numbers here. We're solving for the force on the left side. We got 1 square meter that's acting on. Okay. This ratio represents a pressure that's also the same pressures on the other side. So I wonder how it's going to translate into the force. Right. Well, we're looking at 10 square meters over here. So that's the cross-sectional area on the right side is up to 10 square meters. Woo! So it's like 10 times the area. But the same pressure acting up on the pistons. To hold up a 20,000 Newton weight car. So the force has to be 20,000 newtons. Cross multiply up 1 square meter. You guys see that the left side force is just going to be 2,000 newtons. Interesting. Looks like it's 1/10 of the force. So by, see if I can get these sort of the same screen here. So you can have an input force on the small piston, very small force on the small cross-sectional area. They'll translate to a large force on the large piston because Pascal's principle applies and the same pressure distributes throughout. Now there is a catch. You don't get something for nothing. Let's say that if you press the left piston down, isn't going to displace a certain volume of water, which is also the same volume that is going to increase on the right side. Right? This water doesn't disappear; it just gets pushed over. Which then, if you divide that volume by this very large cross-sectional area, the height change is not going to be very much. So you can push down a lot on the left side, and it's going to lift the car a little bit. But at least you do lift it at all. That's called a mechanical advantage. And you know what's also very similar to? I haven't quite gotten to this part in the class yet. We haven't. Maybe in a few weeks. But you guys remember this mechanism? Showed you guys why that? So there's I rigged up some pulley system. Somehow these strings are routed. Yeah, so that the small weight actually pulls down and pulls the large weight up. Okay, you guys remember that? Now, how is that possible? Well, I'll show you guys that in the future, but for now, just take that to be a fact. But how is that you can get this mechanical advantage? Do you get something for nothing? No, you are paying for this, and the way you're paying for this has to do something with the distances that they move. Look how far that small weight falls down, just to lift the big weight up a little bit, and it does lift it, but it's just a little bit. Okay, see that? Okay. So, so you get an advantage on the forces, and you're paying for it in distance. Very similar to this hydraulic lift. Interesting. All right, so that's a little bit of pressure stuff. Put that to the side for now.
Can you show Pascal principle formula again?
Yeah, Pascal. There you go. The pressure on the left side is the pressure on the right side. And since pressure is just force per unit area, you can say force over area on the left is equal to force per area on the right. That's it. Actually, I do have it. Okay. I'll read this straight off Wikipedia. It says, Pascal's law, also called Pascal's principle, or the principle of transmission of fluid pressure, is a principle in fluid mechanics that states that a pressure change at any point in a confined, incompressible fluid is transmitted throughout the fluid such that the same change occurs everywhere. It was established by French mathematician Blaise Pascal in 1653. Woo! And published in 1663.
So it's a formula to find.
Yeah, force per area is equal to force per area. Okay.
Find force, basically.
Okay, so like back on this hydraulic lift, there's some input force on the left side, like you're pushing down. And there's a car on the right side that has a weight that's also trying to push down. So to hold it up, you have to press up. I mean, pressing down, the fluid's pressing up on both sides. There's some kind of force associated with that. There's also some cross-sectional area for each one that's different. The fact that the areas are different, but the pressures are the same, means that the forces can be different. A small input force can lift a very large object. Okay. There you go. So a little bit of follow-up from yesterday. Yesterday, I took you guys through a ranked choice voting scenario, and well, I'm going to show you guys the results. So you guys voted for Mr. Ortiz, and most of my classes voted for Mr. Ortiz. The only ones that didn't actually voted Mr. Ortiz to the second. So I went ahead and checked his name on that ballot and submitted that. So in case you're curious, there you go. And where are we in terms of our agenda of the week? Yesterday, I went over a bunch of Chapter 4 problems with you guys. Today, we'll hit these Chapter 5 problems. And then we'll finish out this week with a bunch of labs for the next few days. So that is where we are on the agenda. Let's take a look at, we're going to go Chapter 5, start with this one, number 56, and then work on from there. Here we go. And so that's this page. It's the same paper as yesterday. I just printed it on the other side. Actually, I'll do this in the order that I printed them. So we'll start with 83. 83 says you walk so many meters south and then turn and go so many meters east. Find the magnitude and direction of the resultant displacement, both graphically and algebraically. So this is something that you guys have done a long time in here. Chapter 4, what we did yesterday, those were supposedly force in 1 dimension, and this is forces in 2 dimensions. I guess this actually isn't a force question, but it does involve vectors, which is important for 2 dimensions, so good warm-up. So I'm going to change the numbers, but otherwise leave the story basically the same. Let's say you're camping, and there's a campsite here, campsite A, and you leave campsite A, you walk straight south for 400 meters, 400 meters straight south. Then you turn and walk east for 300 meters, 300 meters. And that brings you to campsite B. So there's where you started, there's where you ended up. So that's it, that's your route. So the resultant would represent the straight line path. You could say like as the crow flies, something like that. Here's the resultant, that double arrow, like that. Can you find the magnitude and displacement? It said graphically and also algebraically. So graphically, we've done it. That's the answer graphically. Graphically, you just connect some vectors tip to tail, and then go from the tail of the first one, tip of the last one. That's the resultant. Boom, done. Algebraically means, well, we're going to throw some numbers on this and quantify this. And remember that a vector has 2 parts to it. There's the magnitude, that's to say, well, how far in this case, or like how much can you quantify, but also what direction. So not only do we have to get how long this is, but we also, that's the magnitude. But also say, hey, How many degrees like east of south is that? I bet some of you guys are looking at that right now and already know what the magnitude of this resultant is. Who already knows what that magnitude is? Yeah, Josh.
500 meters.
500 meters. How'd you know it was 500 meters?
It's a 3, 4, 5 right triangle.
It is a 3, 4, 5 right triangle. You guys see that? And had it not been, how in general could you get it? You could apply the what?
Pythagorean theorem.
Yeah, Pythagorean theorem. Yeah. So you could say, well, that would be the square root of 400 meters squared plus 300 meters squared for the whole thing. Right. It comes out to that, but you guys get it because that is a 3, 4, 5 right triangle. Here's one last thing we got to get. We got to say what direction is it because vectors are magnitude and direction. There's the magnitude. What is the direction? Call this angle theta. Well, we've worked with 3, 4, 5 triangles quite a bit here before, so guys, I don't know, maybe you've memorized this by now, I don't know, but there is a method we can use to extract that angle. What's the method that we've been using to extract that angle? Yeah.
Inverse tangent.
Yep. Inverse tangent. You can do an inverse trig. Remember, if you do a sine, cosine, or tangent of some known angle, that will tell you a ratio of, well, two of the sides, depending on which trig function you pick. Or if you know a bunch of side information, which we do, and you don't know the angle, which is exactly the case we have, you can apply an inverse trig function. And I like that you said inverse tan, because that was one I was going to pick too. Inverse tan. Now, if you pick inverse tan, also called arctan, then doesn't that involve the two legs, like opposite over hypotenuse? And so relative to this angle, 300 looks like opposite, opposite over adjacent, that's what I meant to say. Opposite over hypotenuse would be fine for inverse sine, but inverse tan is opposite over adjacent. So opposite of that angle is 300 meters, adjacent is 400 meters. The meters, of course, cancel. Okay, and what is inverse tangent of, well, the radius to 3 over 4? That looks like 36.9 degrees, and that would be east of south. Okay. About 37 degrees east of south. Just to show you this would have worked with the other methods, you could have done inverse sine of 300 over 500. It's also 36.9 degrees. Or inverse cosine of 400 over 500. That's also 36.9 degrees. And so there's 3 different ways to do it. I wrote down one of them. So remember, sine, cosine, or a tangent of an angle spits you out a ratio. An inverse trig of a ratio spits you back out the angle. Okay, next one lined up is, okay, now we're doing 56. So we just did 83. So let's go back and do number 56, which is this one right here. So we'll hit the ones that I circled here, those ones that I signed, and then you'll, as long as you're following along, then you'll at least have your basic homework knocked out. So I got a bonus homework on the table if you want to do that. You know this is all due Friday, right? So plenty of time. Number 90, or why did I do that? 56. I'm so sorry. 56. Says, what is the meaning of coefficient of friction that is greater than 1? If the coefficient of friction is greater than 1, how would you measure it? Okay, so I still have a friction lab lined up for you guys. It's probably going to be beginning in next week, I'm thinking, but coefficient of friction. You guys have seen enough of these that maybe have started to build an intuitive idea of what would be a reasonable coefficient of friction. You guys see numbers like 0.3, 0.4, 0.5, maybe somewhere there. Right? So could it be greater than 1? Yes. Now this is a rare situation, but I'll draw out an example for you guys. So suppose there's a car that's maybe like braking to a stop. So I've got a car. I'll give it a rightward velocity, but I'll say it like V naught, something like that. And I'm going to draw a free body diagram on this car, braking to a stop. Okay. Now this car could have some weight. I'll call that mg. It's going to have some normal force, call it F sub n, which is equivalent to the weight, isn't it? So sometimes it's if it's just a level road, nothing crazy going on. Right, now here's where I gotta draw the friction force. If I were to draw the friction force that long, and I put an arrowhead on that, which I'm not going to, because I'm gonna change that, but what if I drew it that long? Can you guys eyeball approximately what the coefficient of friction would be for this situation? What does that compare to that? Maybe like a third or something, right? Like 0.33 about, something like that. Because you guys remember that coefficient of friction, and let's say this car is like braking to stop, like sliding to stop. Maybe this car doesn't have anti-lock braking or something. Remember, it's defined as the ratio of friction force to a normal force for kinetic friction. Or, if you prefer, I'll write the same thing, just rearrange it a little bit. Friction force is coefficient of friction times the normal force. It's the same idea. Same expression, just rearrange a little bit. So that looks like, yeah, maybe like a third or so. What if you made the friction force like that long? Ooh, doesn't that look pretty close to that? Those look pretty same magnitude, don't they? That would give you a coefficient of friction of pretty much exactly 1 if this and this are the same magnitude. But for coefficient of friction to be more than 1, you need the friction force to be greater than the normal force. So that's the answer. If friction force is greater than normal force, then coefficient of friction is greater than 1. Not impossible, sometimes happens, it's just really rare to happen. There's another question I threw in there. They said, like, how would you measure it? So I'll just tell you guys verbally. I think what I would do is, if you could somehow lift the car, then you could effectively measure its weight. And then you say, okay, well, that could also therefore represent the normal force because of this. So that's how you get that. And then if you, say, tied a spring scale to the car, well, okay, spring scale is kind of silly, but you get it. You start dragging the car, couldn't you measure its pulling force? And if that pulling force was greater than the lifting force, then all this would be playing out. Okay? That's how you could measure that. You guys good? All right, number 90. Yeah, go ahead. Yeah. Go ahead. Yeah. Remember, start number 90, right? It says if you use a horizontal force of 30 so many newtons, I'll change the number for the notes, to slide a wooden crate of some given mass across the floor at constant velocity, then what is the coefficient of kinetic friction between the crate and the floor? So you guys know from this class, whenever you see constant velocity, that means the acceleration is equal to what? 0. There is no acceleration because constant velocity. If there's no acceleration, doesn't that also mean 0 net force? So this block is going to be in equilibrium. Right? Constant velocity is definitely one example of equilibrium. Like on the free body diagram, it might be difficult to tell if it was not at rest, because at rest is also an example of equilibrium. Okay. So number 90, let's get a floor going. Let's get a crate. Oh, wooden crate. This crate has a center mass. Right there. Now let's make a free body diagram for this crate. So, they did give us some numbers. So they told us the mass of the crate, so I'll just write the numbers up here. Mass of the crate. Now, I'm going to make up my own numbers, so I'll say that this crate is like, call it 35 kilograms. And the force to push it, I'll say the pushing force is, let's say it's 50 newtons. 50 newtons to push it. To push it at constant velocity. And that's part of this, right? So at constant velocity. Okay. All right, now let's go see what is this free body diagram going to look like. Okay. So the earth is pulling it down, has a weight straight down. Yep. All right. That. You guys know weight is I've been usually expressing as mg. Now, if the mass is 35 kilograms and g is about 10 meters per second squared, what number is this?
350.
Yeah, about 350 newtons. So go ahead and just write that in. Okay. Isn't there also a normal force from the floor holding that crate up? And how many newtons is that?
350.
Yeah, also 350, just equivalent to the weight. Okay, because level floor, no like crazy tensions pulling in, right? Just balances vertically. All right, now we're gonna push this crate with 50 newtons of force. That looks like about 1/7, I guess, of the weight. Okay, so I'll try to draw it somewhat proportionally. I'll just draw a really small pushing force, F sub push, which was given to be 50 newtons. So that's like a given value. And finally, to finish off this three-body diagram, you were also told that this block is sliding at constant velocity. And that's key because that means that friction force must be equal to what? The same as the pushing force because it has to balance out horizontally. So the friction force must also be 50 newtons. There it is. That's the free body diagram. That's it. All right. Now again, if you did not know if this was static or kinetic friction, then would you know if that block was at rest or not? No, it's possible. Again, like maybe if this was static friction, that you're like pushing against this and it hasn't overcome the initial friction yet, and maybe it truly is at rest. You would only know it's sliding if you know that it's kinetic friction, or if you're told like constant velocity, something like that. Okay. Which is what we have. The question was, what is the coefficient of kinetic friction between this crate and this floor? Okay. Now remember that coefficient of kinetic friction is some material property. No, it's going to be kinetic friction because it's sliding. Okay. So it has to do with materials. So maybe it's like a wooden crate and a tile floor, for example. Right. And then it's the ratio friction force to normal force. So all we got to do is just divide this out. So friction force was 50 newtons. Normal force was 350 newtons. So that works out to, well, as a fraction, it'd be 1/7, wouldn't it? Yeah. And 1/7 as a decimal is like 0.14. 0.14. Yeah. That's the answer. Guys good? And so remember, while you guys are digesting that, just to recap this one. So you were given the mass of the crate and also the pushing force to keep it at constant velocity. That's all you were given. Can you figure out the coefficient of friction between these two materials sliding past each other? So you set up a free body diagram. Then you go to the definition of coefficient of friction, which is the ratio between these two forces. You refer back to your free body diagram that you guys made to figure out what those forces are, plot them in, divide, and get, we'll say 0.14. So friction force is 14% of the normal force. Okay. 14% of the weight. Next question, number 91, says a crate of some given mass is pushed horizontally with a with this given force. Okay. If the coefficient of friction is this number, then can you calculate the acceleration of the crate? Ooh. All right. I'm thinking that this is going to be probably the same type picture that I just made, and maybe a very similar free body diagram, except that this is not going to be in equilibrium, because there's definitely an implication here that there's an acceleration. So kind of what we just did, but maybe a little bit fancier. Number 91. So zoom out. Sorry. Let's get a draw this a little bit off to the left side, because I might want to use the right side of this paper to do some extra math. So there's a floor, there's a crate, center mass kind of like before. What were we given? Let me write all the givens down. We're given the mass of the crate. So I'll just make up a number. Let's say I have a crate that's 300 kilograms. We were given the pushing force, F push. So let's see, I'm going to go with, let's say 1,000 newtons of pushing force, just 1,000 newtons. Okay. And we were also given the coefficient of kinetic friction. So I'm going to call it 0.25. So those are your given values. And we're supposed to find the acceleration. And of course, meters per second squared is going to be the units. Okay? So you find the acceleration with those given values. Well, let's go make a free body diagram, FBD, free body diagram. And then we're going to go to Newton's second law of motion, and then we'll figure out things from there. So this crate has a weight pulling straight down. Call this mg. Okay. And what is its weight equal to? How many newtons?
3,000.
3,000, yeah. Because 300 kilograms times 10 meters per second squared, that'd be about 3,000 newtons. Okay. Oh, well, that means that the normal force must be 3,000 newtons. It's just a flat floor, right? 3,000 down, 3,000 up. That means it's not accelerating up or down, okay, which is obviously true. Okay. Now, we're pushing this crate with 1,000 newtons of force. So I've got a pushing vector that ideally should be a third of the normal force, or a third of the weight. Right. Okay, so F push is 1,000 newtons, right? But the friction is not necessarily also 1,000. The friction could be 1,000 if you knew that the crate was in equilibrium. But the implication is that that's not the case, because we're trying to figure out what acceleration is. So we've got to use a different method than we did before to figure out what the friction force is. So if you think about this, 300, okay. I'm going to do a little tiny friction force right there. Call it force friction. Okay? Friction force. Okay. Oh, maybe somebody out there has already calculated it. Has anybody already figured out what the friction force is equal to? Does anybody know out there? Okay, let's set an equation and go solve this way. You guys remember that friction force is equal to coefficient of friction times the normal force? You guys remember that? And just for completion too, you guys remember on the very first day of school, this is one of the pages that I gave you guys, and then we're on forces and Newton's laws, and this, it's one of these equations right here. Friction force is coefficient of friction times the normal force. Okay, so handy page to have. We know some of these values. The coefficient of friction was given. Coefficient of kinetic friction, 0.25. So that means that the friction force is 25% of the normal force. And the normal force, well, that must be equivalent to the weight. Sort of reasoned through that already, because the forces in the y direction have to zero out. So that's 3,000 newtons. So what is 25% of 3,000 newtons? Say 0.25 times 3,000. I'm looking at 750. So the friction force is 750 newtons. Now, that's not what was being asked, but that's an important middle step. So go over here, say, maybe I'll change ink color just to say that we did do a bunch of work to solve this. 750 newtons. You guys see that there is a net force on that block? Now, I just made up some numbers from scratch, so I didn't know exactly how this was going to play out, but is that block speeding up or slowing down? What do you guys say? It must be speeding up. Yeah, here's how you know. The fact that friction force, kinetic friction, always opposes motion means that the block must be moving to the right. So it's moving to the right. There's also a net force to the right because you're pushing more than the friction. You guys see how there's a net force of 250 newtons? So yeah, that block must be speeding up to the right because its acceleration and its velocity are in the same direction. So the net force must be the difference between these two. So just more work down here. Let's go. We're getting really close to Newton's second law of motion, aren't we? So net force is equal to the pushing force minus the friction force, which is 1,000 newtons minus 750 newtons, which is 250 newtons, which again isn't exactly what was asked, but you do need to figure that out to answer the question. And the question was, what is the acceleration? Okay, so now we're down to the very last line. Here's Newton's second law of motion. The acceleration of the block is net force divided by mass. That's just straight Newton's second law of motion right there, isn't it? Net force acting on some mass will result in some acceleration. The net force, well, we just did that as a side step. It's 250 newtons. There's a 250 Newton net force acting on the block of 300 kilograms, 300 kg, Newton per kg. Let's see what that works out to. There's 250 on 300. I'm looking at 0.83, 0.83, and Newton per kilogram is the same thing as meters per second squared, which describes acceleration, and that answers the question. Okay. So while you guys are finishing writing that down and digesting that, I will recap this problem real fast. You were given the mass of the block in kilograms, the pushing force, and I guess you also happen to know what the coefficient of friction is between these two materials. Let's say between this wood crate and whatever the floor is made out of. It ends up being like 25%. Okay? And given those values, there is enough information lying around that you can figure out the rate that the block is speeding up, that it's accelerating. It could have been slowing down, but in this case, it ends up being good. Okay, so make a free body diagram so that you can label all the forces. Well, it's got the weight down, m times g, so mass times g should be the weight. The normal force must be counteracting that, so it's not accelerating up or down. The pushing force was one of the given values. And you don't know friction force right away, but we can do a little bit of side math over here and say, well, I know that the friction force is 25% of the normal force because both of those things are known, both those values. So we can figure out a quantity for the friction force. We got that. Boom, boom, solve that. And now we're getting really close to being able to figure out what we want to find. Because you can figure out the net force on the crate. Vertically, it's just 0, but horizontally, it's the difference between these two. Figure out the net force, which is this many newtons. And finally, take that net force, divide by the mass of the crate, which was one of the given values back at the beginning. And that will give you the acceleration. Okay. You guys good? Okay. Number 97. Advertising. Joe wishes to hang a sign weighing, yeah. 7.5 times 10 to the 2 newtons. Ooh, that's a scientific notation, isn't it? The reason that they give us, or one of the advantages of spelling it out this way, is that you know that 0 right there, 7.50, that 0 is significant. So you know it is exactly 750 newtons, not 753 and rounds down. No, 750 exactly. Cable A is attached and makes a 30-degree angle with the vertical, as shown in this figure. Cable B is just straight horizontal. Ooh, interesting. And the question is, what is the tension in cable B? Now, when I solve this, I'll go ahead and solve for the tension in each cable, so you'll know both of them. And then, like before, I'll change one of the numbers. Actually, I'm just going to change the weight of the sign, but I'll go ahead and just leave the 30-degree angle right there. All right, so this is number 97. All right. I'm going to put a dot right in the middle of the paper. So I'm going to make a huge free body diagram that's going to take up the whole paper. Let me introduce a coordinate system that runs parallel perpendicular to gravity in the ground. So here's a Cartesian. system. And this dot, I'm going to let that be the place where everything comes together, where the two cables come together and the sign's also hanging from that point. And say that this point has three forces that are acting on it. It's got the weight of the sign pulling straight down. So I'll call this mg. Okay. Now they said 750 newtons. I'll just round that up to an even 1,000. Let's call it an even 1,000 newtons. 1,000 newton sign, which is mass of 100 kilograms. So it's kind of like if you had 100 of these. I guess that's a pretty heavy sign, right? It's like 100 of these. And there's a cable that's pulling up and to the left at 30 degrees from the vertical. I'll call that T sub. They call them A and B, right? Okay, so I'll call it T sub A, like the tension in cable A. And then there was the other cable was pulling straight horizontally. Now this horizontal cable I'm going to represent with a very small magnitude tension force. I'll call it T sub B. So I know already just from teaching this class for so many years that the tension cable A is going to be much more than the tension in cable B. How do I know that? Well, I know that you'll see it right away once you break tension A into components. We're going to make components that align with this coordinate system. Luckily, the weight and tension B are already aligned to the coordinate system. So there's only one that we have to break into components. That's cable A. So I'm going to say cable A is pulling up and to the left. How much up and how much to the left? Oh, well, that's a question that you guys have been working with since the very beginning of this class, even before we did kinematic motion, to have you guys break components and vectors into components. Okay. Right, now, here's how I knew that tension B was going to be really short. However much left tension A is pulling, tension B has to pull right exactly that much so that it balances out horizontally. Guess it? It's going to balance out horizontally. Okay, so got like the same magnitude going on there. Oh, I forgot to write in the angle. This was 30 degrees, or this was 30 degrees, depending on your perspective. Okay. So isn't this component right here equal to tension A times sine of 30 degrees? Because it's opposite of that angle. And therefore, the vertical component would have to be tension A times cosine of 30 degrees. Is that true? Guess that? That's all right? So we got ourselves a free body diagram, FBD, free body diagram. We know what the weight of the sign is pulling straight down. We know the directions of the two cables, and we took the one that's diagonal and we split it into components because that's a good your first step to do. All right, so we are well on our way to solving this. The conditions that are going to set up, this is equilibrium. It's in equilibrium because, I mean, it is at rest, which is an example of equilibrium, which means that there's no acceleration and there's no net force. So the net force, the sum of the forces, is equal to 0 newtons. And that's true both horizontally and vertically. That's why we got this Cartesian system and we broke into components. So the sum of the forces in the x direction and also the sum of the forces in the y direction must each be 0. Ooh, let's do that. Oh, I'll let you guys know, just in case you're going to be an engineer or something one day, how this eventually expands. So say you're like building a bridge or something, you would also have to say the sum of the forces in the z direction, like into and out of the paper, must be 0. And also torque. So we haven't talked about torque yet. It's like a turning moment. It has to do with like opening a door. If you've ever wondered, why is the doorknob opposite of the hinges? Because if it was close to the hinges, it'd be really hard to open the door. That's a torque concept. So that's in the future. But for right now, we've just got the sum of the forces on each of the two axes on this xy plane must 0 out. All right, so. All right. That's all good. All right, so I'm going to start with the vertical stuff because I already know some vertical information. So let's do that. Sum of the forces in the y direction must be 0 newtons. Therefore, I know that tension A cosine 30 degrees acting up must balance with the 1,000 newtons acting down. Okay. So tension A times cosine of 30 degrees if that's its upward component. Technically, you'd say this, minus 1,000 newtons is equal to 0. But just add 1,000 over, same idea. Okay. Tension A times cosine of 30 degrees is equal to 1,000 newtons. Divide both sides by cosine of 30 degrees. You guys know that algebra stuff, right? So here, divide by cosine of 30 degrees. Do that to both sides. Algebra, balance it. We've done that many times in this class. Gonna cancel out on the left side. Yeah, tension A is equal to, what is 1,000 newtons divided by cosine of 30 degrees? That's looking like tension A is 1,155 newtons. Or actually rounds down to 1150 to 3 sig figs. If you heard about sig figs, you might say like 1150. Guys good? All right. The book actually asked for what is the other tension. So I said I would do both. So there's one of them. Well, now that you know tension A, there's multiple ways that you can solve for tension B. One way to do it, well, you guys see tension B is just going to be equal to tension A times sine of 30 degrees. Right? This has to equal this because the sum of the forces in the x direction must also zero out. Therefore, I'll just cut to the chase here and say the tension B that we're solving for must be equal to tension A times sine of 30 degrees. Right? This has to balance with that. The right has to balance with the left. And since you know tension A, all you have to do is substitute that in. So if you take the answer from the last one, 1,100 and something Newton, 55 Newton, multiply by sine of 30 degrees. Hey, sine of 30 degrees, does anybody remember what that is? It's equal to a half, exactly. Okay. So this ends up being 577 newtons. That's tension B. That's the horizontal cable. Horizontal cable is pulling straight to the right with 577 newtons. Right? Let's go back to the original picture. Let me see if I can put these side by side in the same frame. Zoom out as much as I can here, as much as I can zoom out. Let's see, I think it's showing up on the camera okay. So there's the answers on the left, there's the setup on the right. There are multiple ways to work your way around a triangle, you guys know that. So I'm going to do one more check. Do you guys remember a tangent of an angle is equal to the ratio of the two legs, opposite over hypotenuse? What that means is I should be able to take, opposite over adjacent, that's what I meant. Opposite over hypotenuse is the sine ratio. Opposite over adjacent is the tangent ratio. So if I start with the leg that's adjacent to this 30-degree angle, which is supposedly 1155 newtons. Oh, no, it isn't. It's 1,000. I'm being silly. This is 1,000. I want to show you guys the other way to also solve this. Scratch that. 1,000 newtons. Right? Because the diagonal was 1155. So the upward part is exactly 1,000 because it exactly matches that. So this is 1,000 newtons. If you were to multiply by tangent of 30 degrees, that would translate it from the adjacent leg to the opposite leg, which is a different approach, but it should also tell me exactly this number. Right? Let's see if it does. Is this leg times opposite over hypotenuse of 30 degrees, that's say tangent 30 degrees, is that equal to 577? Yes, it is, 577 newtons. So there's different ways to solve that. All right. So we just got through at least the basic type homework problems. You guys got any questions about any of those? Any questions? All right. So that's the end of class. Tomorrow I'll set you guys up with a bunch of pulleys, some strings, some weights, and you guys will have some Atwood machines.